Okay, so last video we looked at the integral of e to the x, okay? In this video we're going to look at a kind of different function. So do you remember the power rule? The power rule for integration said that the integral, the indefinite integral of x to the n dx equals x to the n plus 1 over n plus 1 plus c, where n is not equal to -1. Now we're going to learn the case where n equals -1. So finally, we're going to be evaluating this integral. The integral of 1 over x dx. And that is equal to ln x. This is so important. Now you can integrate lots of different types of rational functions. Okay, this integral allows you to integrate rational functions, which you can, which expands the types of functions you're allowed to integrate now. With the power of rational functions and this integral, now you have a whole other set of functions that you can integrate. Okay, so let's look at a couple, okay? So one of the first types of integrals you learn are the easy ones, okay? So let's look at the integral of 1 over 2x plus 3. So under normal circumstances, this integral would have been impossible to evaluate. But now with this integral, all you need is a simple U-substitution with u equals 2x plus 3. So if u equals 2x plus 3, if u equals 2x plus 3, then we need a 2 at the top to make that du. So we can introduce a 2 by multiplying the integral by 1/2, and you get 1/2 times 1 over u du. And that is equal to ln. ln of u equals 1/2 ln of 2x plus 3. And I should point out, this is an absolute value, okay? Because the ln function is only defined for positive values. Okay, so x must be greater than 0. Because why we put that absolute value sign over here? Okay, so I forgot to mention it's a big part, okay, that you have to put this absolute value sign in order for the ln function to be defined for all real numbers. Okay, so let's do another one. Let's do the integral of x over x squared plus 1 dx. So now you have x squared plus 1. Okay, so let's make this your u. Okay, because du is just 2x dx. So we just need to introduce a 2 by multiplying by 1/2. And this is equal to 1 over u du. 1 over u du. And this equals 1/2 times the ln of x squared plus 1 plus c. Okay, simple. Now, let's do this one. Okay, e to the x minus e to the negative x over e to the x plus e to the negative x dx. Now this one certainly seems complicated, but it's not really that complicated if you use the ln rule. Okay, so there are actually two ways to go about this integral. Okay, and that stems from the fact that you can let either the numerator or the denominator equal to u. Okay, which is kind of confusing. Okay, but if we let this equal to u, then du dx is equal to e to the x minus e to the negative x, which we have in the numerator. Or if we let this equal to u, we have du dx equals, that equals e to the x plus e to the negative x. Okay? But you have two possible choices, okay? And they both look good because the derivatives match each other. However, the only plausible one would be the bottom. Why? Because this, if you were to turn into du, would require that e to the x plus e to the negative x is in the numerator, which is not. So this choice is bad. So we're not going to focus on this choice. We're going to focus on this choice. Okay, and we let du equal e to the x minus e to the negative x dx. And that again gets you 1 over u du. We didn't even have to introduce anything. And that gets you ln of e to the x plus e to the negative x plus c. Now, there's so many different things you can do with this ln function, okay? So many different types of integrals. So we're gonna, remember when we did those trig integrals? Okay, we got the integral of sine x is negative cosine x. The integral of cosine x equals sine x. The integral of secant square x equals tangent of x. You can assume there are constants of integration for all of them, okay? The integral of secant x times tangent of x, that equals secant of x. The integral of cosecant of x times cotangent of x equals negative cosecant of x. And the integral of cosecant squared of x equals negative cotangent of x. Okay, you might be wondering why I'm writing these. Because when we were first introduced to these, you're probably wondering why these ridiculous values rather than the normal 6 trigonometric functions. And that's because these functions have an easy antiderivatives because they're derivatives of the 6 basic trigonometric functions. You can see that the antiderivatives make up all 6 of the basic functions. But using the ln, we can find integrals of stuff like tangent of x dx. Let's do that right now. Now, tangent of x can be written as sine of x over cosine of x dx. Now, we can let u equal cosine of x. That means if u equals cosine of x, then du equals negative sine of x dx. So we need to introduce a negative sign. That happens when we multiply the integral with a negative sign to maintain the equality of the integral. So this simplifies to 1 over u du, and that gets us negative ln of u or negative ln of cosine of x plus c. So we just got that the integral of tangent of x dx is negative ln of cosine x plus c. Now let's look at the integral of secant of x. Now, there isn't really an easy way to do this one okay? And that is because if you express this as a reciprocal trig function, that does not do anything at all, okay? Because the derivative is nowhere in the function. You can't let u equals cosine of x since the derivative is nowhere in the function. So what you do is a very sneaky looking trick. Kind of sneaky looking trick. So if we get the integral secant of x dx, what we can do is multiply this, both the numerator and the denominator, by secant of x plus tangent of x. And this is incredibly sneaky, okay? So usually you won't get it right on the first try. But what this does effectively is it creates a situation in which it's ideal to use U-Substitution, okay? Because if we distribute secant of x to the numerator, look what we get. We get two very familiar looking derivatives. And on the bottom, we get their antiderivatives. So what we have is an ideal situation we created for U-Substitution. So if we let u equals secant of x plus tangent of x, well, the derivative du dx is right in the numerator. Okay, you can actually check this. So we can write this as 1 over u du. That gets us ln of secant of x plus tangent of x plus c. Okay? You could do a very similar trick. So here. You could do a very similar trick for the cosecant function. Okay? And you get the ln, negative ln of cosecant x plus cotangent of x plus c. Cosecant of x plus cotangent of x. So now we have 1, 2, 3, 4, 5, 6. So we have okay, I forgot cotangent of x. And you can use a similar derivation technique to find the derivative of cotangent of x as tangent of x. So cotangent of x is cosine of x over sine of x. So using a similar technique, you get ln of sine of x. Positive ln of sine of x plus c. And if I were to select and delete all of this mess, you would see that you now have integrals for every single trigonometric function, every single one of the basic trigonometric functions that you can have. See, sine, cosine, tangent, cotangent, secant, and cosecant, as well as some other ones that result from antiderivatives. Okay? So you can use this to find lots of things, okay? Lots of things, such as the area of under f of x equals tangent of x from 0 to pi over 4. Not pi over 2, because that's kind of illegal. Okay? And now using our new rule, we can write this as negative ln of cosine of x taken from pi over 4 to 0. And we get negative ln of cosine of pi over 4, which is root 2 over 2, root 2 over 2, minus negative ln of cosine of 0. Cosine of 0 is 1. Cosine of 0 is 1, and that gets a 0. Okay? So we have negative ln of root 2 over 2, which equals this. If you know where this comes from, it becomes very easy to change this into a positive log. Okay, you can just use log properties. Here. Okay, so here's a little better way of writing it. Okay, you can also write it like this. Now here is the area under f of x equals tangent of x from 0 to pi over 4. And I cannot understate the importance of this integral enough. So what we're going to do is do another. We're going to get another integral. Okay, and that requires let's take the integral, and this requires another technique. So x cubed minus 3x squared plus 4x minus 9 over x squared plus 3 dx. Now, how would you go about doing this? So you certainly can't let anything equal u, since the two functions, their derivatives do not even match. Okay, they don't come close. So what would you do? Well, if you remember way back in algebra class about polynomial division, then it will really, really help. So let's divide these two polynomials using the long division, okay? So here we're going to multiply by x, and we get x cubed plus 3x. Yes? So this cancels, and we have x. So negative 3x squared plus x minus 9. So we can do minus 3. Okay, so we have minus negative 3x squared, negative 3x squared minus 9. So this cancels, and we get 18. And now you're left with whoops. Wait a minute, you're just left with x, okay? Let me just check if I did all this right. Looks like I did. Canceled, it's also canceled. Yeah, x. So this you can write as x minus 3. You can write as x minus 3 plus x over x squared plus 3. All that dx. Okay, so we just divided the two polynomials by each other. This is our remainder. And you could write it in rational form, and now it looks a lot easier to integrate. Okay, so you have x squared over 2 minus 3x plus, well, how do you integrate this? Well, you can simply introduce a 2 and get 1 over u du. You get 1/2 ln x squared plus 3. So you have plus 1/2 ln of x squared plus 3 plus c. And we are done. And we're done. So this integral is one of the most important that you will learn. Okay? Just, you cannot understate its importance. Okay? Because now you have rational functions that you can integrate. Okay? So you extend the amount of functions that you can integrate by introducing this integral, the integral 1 over x dx. Thanks for watching. Make sure you comment if you have any questions, like this video, and make sure to pass it on. Thanks for watching.